Good job on the midterms, and I have them up here, the graded ones. After the lecture, you can come get it. You can also, I have 2 copies of the solutions. They need to stay in this room, but you can look at them. They have the questions and the answers from the midterm. Okay. Today we're going to start by talking about some interesting applications of the Fourier transform. You can first enjoy my joke if you want. Well, not my joke, but a joke. The applications we're going to talk about are not things you're going to be tested on. It's just so that you can see some of the interesting areas. Actually, they all have to do with imaging and medical imaging, and we'll see how the Fourier transform plays a role in that. Before we do that, let me just define for you the 2-dimensional and 3-dimensional Fourier transform. We've already done these in the lab, but we've never mathematically talked about them. They'll be useful to have a definition of these as we talk about these imaging techniques. So here we have a 2D Fourier transform. We're assuming we have a 2-dimensional signal. I'm not going to use x as the signal name because now I want the dimensions to be x and y. Okay, t was our dimension for 1D signals. I'm going to use x and y as the variables for 2D. So we have something like an s of xy is some function, some signal, and we're going to talk about its 2-dimensional Fourier transform. And that's simply going to be, we would say like a capital S of, now it's going to have 2 frequencies, fx and fy, and this is just going to be a double integral of s of xy e to the negative I 2 pi, and we have 2 terms up here, fx times x plus fy times y. All right, yep, that's it. And we take the integral with respect to x and the integral with respect to y. Okay, and the inverse is exactly the same thing with the minus removed. So s of xy equals the double integral of capital S. And it's just a e to the positive I 2 pi. Same thing up here. Now, one thing you can notice here is that, whoops, it should be dfx, dfy. One thing to notice is that this term in the exponent can be thought of as a vector multiplication. So we can take this thing here, and we can say, well, that's just a vector. We can say f is a vector. Fx, fy, and our position is a vector. Let's say position equals xy, and we just have this is f transpose p, right, in the exponent. So so if we want to think of these as inner products, like we like to think of the Fourier transform, what we have are complex exponentials, but these are plane waves, okay, in 2 dimensions. So what that means is we have a f points a certain direction. So we've got something like this. There's x. Here's y. And we have f points in some direction like this. And we have plane waves then that look like sinusoids along that direction. And it's hard for me to draw a plane wave, but I'll do my best job here. And the peaks line up perpendicular to that f vector. Okay, so there's a plane wave in the direction of f, of the f vector. The longer f is, the higher the frequency, so these peak wave fronts should be closer together, right? Now, again, I've sort of cheated here because this is a complex exponential. That's a complex valued function. and I'm plotting it in 2D, so I really would need a 4-dimensional plot. I would need one for the real part, one for the imaginary part of the function value, and 2 dimensions for the arguments, okay, and I can't really plot that. So I've drawn these like sinusoids because we know how to interpret complex exponentials as sinusoids, right? Okay, but really it would be a complex, in this direction, it would be a complex exponential. All right, not a sinusoid exactly. Okay, now another nice way to think about the 2-dimensional Fourier transform is that if I rewrite it here, I can rewrite it as S of fx fy is I can do one of the integrals first. So I've got okay, you see that this is just a nice consequence of the exponential being a very nice function. It separates out this way. So if we bring it in, we do one integral first, and you can see that you can think of the 2-dimensional Fourier transform as being first, treat y as a constant. Just look at these as signals in terms of x. Just look at the x direction. Now you have a whole bunch of them, one for each y, right? For each one of them, take the Fourier transform. We get a new signal. It's now in frequency domain. So replace each of these with its Fourier transform, and then switch the direction. Now now take the Fourier transform with respect to y. So it's like you transform in one direction first, then the other. And that's the same as the 2-dimensional Fourier transform. So it's very nice. It's got all sorts of rotational symmetry and stuff, so it's really easy to work with. We could then, of course, go to 3-dimensional Fourier transforms the same way, right? It would be, you could think of it as taking the transform in one direction, then another dimension. Or you could think of it as plane waves along arbitrary directions and looking at inner products. Okay, so now let's get to the MRI application. Okay, so how did the Fourier transform save lives? Actually, I should do this. Let me first just introduce MRI to those who may not even be familiar with the acronym here. Let's see if we can get the Wikipedia page for MRI here. Okay, so MRI is magnetic resonance imaging. It's a way of taking images, often of a human body, but it could be all sorts of things. 3-dimensional images, and we're going to look at sort of a 2-dimensional representation of 3-dimensional image. Here's an example. Someone's head is scanned in an MRI machine. Now, first of all, let's look at a picture of an MRI. Here's one that you would encounter like in a hospital. Can we get that bigger? Okay, you get that what needs to be imaged is placed in the center here. Does anyone know what this big device is? Yeah, it's a big, huge magnet, electromagnet, usually, right? What? Has anyone had an MRI done? Had a couple? Okay. I've never had one done. Does it take a long time? I hear it does. So your leg was in there for like 30 minutes. Yeah. So that is one of the complaints about MRI, is it generally takes a while. There are some very good things about MRI compared to other methods. There's another imaging device that looks something like this, but it's not MRI. What do you think I'm thinking of here? Yeah, I heard, well, okay, fMRI is MRI, but it's for various purpose. But I heard CAT scan, right? CT. And we'll talk about that as well, which uses X-rays. Very different way of getting the image. Completely different. But let's start with MRI. One of the nice things about MRI versus CAT scan is that you don't have dangerous radiation being used in MRI. It's not ionizing radiation, so it should be doing no harm to your body, whereas if you have too many CAT scans, it can actually be cancer-causing. So let's see now a cool image here that you might get from MRI on the head. So what's happening here is they're moving along different slices of the head. And you're seeing a 2-dimensional image as you move through. Because really you construct a 3-dimensional model of the object, but you need to view it somehow. Right? I want to see that one more time. Passing through a human head. there's one artifact that they point out here, that the nose wraps around to this side, or the forehead and the nose. Did you see that? And there's a mathematical reason why that happens. We'll talk about that for a minute. See, the nose popped in there. Okay. So these slides that I have are courtesy of a couple of people. One is John Pauly at Stanford, and one is Neil Bangerter at Brigham Young University. And I'm using their slides that they shared with me. They actually do research on MRI imaging. So like I said, the advantages of MRI, it's non-invasive. You don't have to open up the body to image it, and it's non-ionizing radiation. And you have a lot of control over how the imaging goes, and you'll see that in a minute. You generally, the idea is you need to get some sort of contrast in the body. So the contrast that MRI usually is used to pick up is water content. Okay, so MRI, the vanilla case that I'm going to show you here, of course there's a lot of variations of MRI, but the vanilla case is that hydrogen atoms are what you observe through the medical imaging, and these are in water. So where there's more water, you're going to see a brighter spot in the image. Okay, but then you can do all sorts of tricks to get contrast in places that wouldn't naturally have contrast there. Here we see a brain and a knee, I believe. Okay, so the idea is that atoms that have unpaired protons or neutrons have a magnetic moment from their spin. Okay, so hydrogen is one such case. Now these spins are going to just orient somewhat randomly, usually, but if you put them in a magnetic field, okay, then they're going to line themselves up with the magnetic field. And think about these spins as being a little motion of electricity, okay? And what happens when you move say, an electron through a magnetic field? What? It curves, right? It could go in a circle, for example. Okay. Well, so what's interesting, the way that you're going to get an ability to image out of this is that as these molecules or these atoms go to line up with the magnetic field, they don't just go straight there. They actually precess. Let me see if. So they actually precess. In other words, they rotate around as they converge towards pointing in the direction of the magnetic field. Okay, you can think of this like a spinning top. As it falls down, it's eventually going to fall, but as it falls, it starts to precess. And the frequency can actually be calculated nicely. What frequency it's going to be rotating around as it straightens itself up towards the magnetic field. Okay, this is referred to as the Larmor frequency, and it just depends on the strength of that magnetic field and the particular molecule, but we're assuming it's all hydrogen that we're dealing with here. Okay, so you have a particular Larmor frequency. Now, the cool thing is, as it goes around and lines itself, it actually radiates electromagnetic waves at that frequency because it's losing energy, and whenever it loses energy, it needs to give it off somewhere, right? So it radiates it outward. So you would actually, if you put an antenna, maybe that's on the next slide here. So yeah, if you put an antenna, well, first of all, they're saying, how do you get it? Forget about listening to it for a minute. Once it's lined up, and this only takes, probably, I don't know the order of time, but nanoseconds maybe that it lines up, okay? And once it lines up, then it's quiet, right? It's not radiating anymore. But you can knock it out of alignment again. So if you put a little antenna and you send out a pulse that's around its Larmor frequency, then it'll go out of alignment again and then come back in. Okay, and so that's how you excite this. So you put a little RF antenna there in the MRI machine and send out a little pulse that knocks it out of alignment, and then it's going to come back in and it's going to radiate on its way back in. Okay, so you're going to be able to use this antenna both to excite it and also to listen to it as it emits this radiation, as it emits these waves as it lines back up with the magnetic field. Now, I have an analogy that I think works very well here. Maybe I'll say it now. Of course, the physics is very nice to understand, but the mathematics are almost identical to the following situation. Suppose that each little particle that you're trying to image is a little string, and the magnetic field is putting tension on that string. Okay? And when you pull a string tense, it wants to just sit there without vibrating, but if you excite it, then it's going to vibrate at a known frequency. And if you make it more tense, it's going to go to a higher frequency. Exactly like this. The stronger the tension, the higher the frequency. They're proportional. And so, what you can think of is all of these little particles are in some space, and they're being pulled tight by this magnetic field. Their strings are being pulled tight so that they would resonate. Okay, and the idea is you're going to excite them. Everything's quiet, right? You're going to excite them by puffing in some air. Imagine a room full of string instruments, and something explodes, outside, and all the instruments start making noise, right? They start humming for a little while, and you can listen to them. Okay, so that's the idea here, and you can keep that analogy in mind if you want. Okay, so as we said, we have this big, huge electromagnet that you get placed in. Okay, and I'm going to skip that one. Let's see. So everything's lined up. Then you excite it, and everything starts spinning together. All right. So mathematically, you can say that you're getting what you should be hearing. Let me see if I can write on this slide. So you should be hearing some constant that it has to do with the amount of material in the space times some frequency that's singing back to you, right? E to the I 2 pi. And the frequency is proportional to the magnetic field. So gamma is just some constant of proportionality that tells you what the frequency is, multiplied by this magnetic field, B naught, and then times time. So you're getting some signal like this. I'll say S of t equals this. Now, so m is just representing the total, maybe mass or whatever, somehow representing the amount of material in there that's singing back at you. Now, why am I saying this is a complex signal? Okay, I know we use complex numbers in the math that we're doing in this class, but why should I say that the signal you receive on your antenna is the complex value? No, it's actually some sensor. You're actually picking up voltage on an antenna. So, you're picking up the current on the antenna. So why can I say it's complex? Well, it turns out that this signal is polarized in a certain way. And so you actually are getting two different signals that you're able to pick up. And if you treat one of them as a real part and one of them as an imaginary part of a signal, I mean, of course, they're both just real measurements, right? But the math works out just great here that if you treat one of them as the real part of a signal and you call the other one the imaginary part, you put them together as one signal, then this is actually what you receive. You receive a complex exponential like this. Okay, so this is one of those cases where, and there are many of these, where you can actually consider a signal to be complex even though you got it from real sensors because you just constructed it somehow from different sensors. All right. Okay, so you receive something like this. Now, so the problem here so far, how are we going to actually image? So all we have now is a way of maybe getting an idea of how much total hydrogen there is in the space, right? How loud is the sound coming out? How do we figure out where it is? Because that's what we need for an image. And that's where the real trick comes in. What you do is you put a gradient magnetic field. So you have another device inside this electromagnet that allows for a much smaller than B naught. B naught's some huge magnetic field. But anyway, it allows for causing more magnetic field along one direction. As you move along one direction, the magnetic field gets slightly stronger and slightly weaker. So that's a gradient. Here we're drawing that, let's say this is the x direction. You have a gradient along that direction. And that gradient is going to cause the different strings to be tightened to different tensions, right? So they'll be tuned to different frequencies. So things up here will be at a higher frequency, and things here will sing at a lower frequency. And that's the whole key to differentiating where the material is. All right, so I'm going to take a break from this slide and draw a one-dimensional case. Okay, so let's get out of this. All right. Okay, so imagine now that what we have is some density function of along. Now we just are imaging in one dimension, so I can draw things and we can see the math very nicely. All right, so along this line, we have some particular line, and we want to know how much hydrogen is there at each point along this line. So I'm going to say that there's some density function. This is d of x, and that's what we want to know. Okay, we want to know d of x. But what we actually are able to do is when we now apply we have a magnetic field, B naught, plus, let's say, some gradient times x. So it's just a linear, the magnetic field is just a linear function of x. Okay. Now what we're going to hear back, S of t, will be the combination of all of the singing from all the different parts of the choir, right? So we have an integral of this density, and each part of this, each piece of material is giving me back a signal that's I 2 pi, and it's gamma times the magnetic field, right? Times t. Now I integrate over x because my antenna that's receiving this is just combining all of the signal from every point in the space, right? So this is what I get back. Let's rewrite this. I'm going to pull out this part, the I 2 pi gamma b naught t. That pulls out of the integral. Okay, does anyone recognize another way to write this integral in terms of something we've named and discussed in this class? So what is this integral here? It's an inverse Fourier transform of d, right? So let's say, let me keep this first part. And this is a inverse Fourier transform of d of x. Now, d of x is being interpreted. An inverse Fourier transform, we usually think of some function of f. It doesn't matter what the argument is, right? It's just a function. This is an inverse Fourier transform of that function d. Times, but it's not exactly. It's evaluated not at the point t, but it's evaluated at the point gamma g t. Right, so it's an inverse Fourier transform of d, but then you substitute the argument with gamma gt instead of just t. You see that? So what that means is that we can reverse this whole thing. We can say that d of x equals, what we're going to have is an s of t over gamma g. And that scaling is not going to be crucial for this, but anyway, we've got t over gamma g, so it's just a rescaling of what we measured. Then we just multiply by this thing, which is just it's really going to serve as just shifting in shifting d, because remember that if you multiply by a complex exponential before taking a Fourier transform, you just shift. Okay, and then it's the Fourier transform, right? Is this correct? I think so. So we get back what we wanted to image by just taking what we measured. So it's pretty incredible that this application is perfectly tailored for the Fourier transform. We just take what we measured on our antenna. We have some squishing in time. Okay, not a big deal. We multiply by something, which, remember, that's just going to, remember our Fourier transform properties, that if we shifted this in space, if we shifted along x, that's equivalent to multiplying in the frequency by, or sorry, if we shift in frequency, that's equivalent to multiplying in time by a complex exponential. So this is not, to understand this conceptually, this is not that important. But you multiply it by some signal, and then you take the Fourier transform. Okay, I guess what I mean is, had you not done this or this, you would still get the same image. It would just be either compressed and shifted, perhaps. Okay, but otherwise it would be the same image. So voila, nice, huh? You use the Fourier transform to do MRI. So let's look at the. Let's look back at. Actually, let's talk about this intuitively for a second. So we looked at the math, intuition. Think about having a bunch of points that are individual molecules, and some of them are close together and some are far apart. Okay, so our density that we were trying to image before was just sort of a cumulative distribution of these things. It was just representing these point masses as a density, right? So, but now, if you think of them as individual points, think of these as little strings that are each pulled to a different tension, right? And because you have the frequency, so you have the frequency change with the space. So you've got this material, and you have no way of viewing what is where. Okay, you just have a way of exciting the strings so they start vibrating back at you, and you want to tell where they are, right? You don't know where they are, but you do have a mechanism for making sure that their tuning depends on their spatial location. Okay, so in this case, we make it linear, right? So the frequency, this is the frequency, and it depends on where they are. So even though you don't know what's there, you can at least, by setting the magnetic field, cause the frequencies to depend on their location. And then you just record what's there, and if you hear a lot of high pitches, then you know there's a lot of material up in the high pitch range, right? And so in this case, you would hear a lot up in this range of frequency. You'd hear a lot down here. You'd hear a lot down here, and nothing in between. And of course, we can separate that out with the Fourier transform. That's how we would tell where things are, right? Okay. So it gets a little more, when you actually do this in practice, there's a few other knobs to turn and ways to make the design interesting. For example, a couple of, let's see. Okay, so a couple of things. First of all, they don't keep the gradient fixed. You have a lot of control on this gradient. You can change it with time, even while you're doing the imaging. So they use a time-varying gradient. And when you have a time-varying gradient, then you actually have, so we can call this g of t, the gradient at each moment in time. You're changing it with time. Then what you're actually getting back instead is an integral of this density, and what you get back is I 2 pi, but instead of the formula we had before, this just becomes an integral. Oh, it's a gamma, that's the proportional constant for the Larmor rate. An integral over time of b naught plus x g of t. The gradient is a function of time. You integrate this with respect to time. Okay, and of course, if g of t is constant, this is going to get us back to the exact formula that we had right here, this formula, right? But if it's not constant, you can get it to give you other things. In particular, you use this time-varying gradient because you're doing a high-dimensional imaging, and we were just talking about one-dimensional imaging, in 2 dimensions and in 3 dimensions, you want to use this time-varying gradient to give you interesting. I'll show you. You want to use the time-varying gradient, as they show in this picture, to get different samples of the Fourier transform. So here they're showing what would actually be done in practice. You would have a gradient on the in the z direction when you excite it. This allows only a small region to actually be excited. Then you would actually have a gradient in one of the directions, the y direction, only before you start measuring the output, and then you have a gradient in the other direction. And anyway, these time-varying gradients allow you to do something different than what we said. We said that what you measure is the Fourier transform of what you want to image, right? What happens here is, in 2 dimensions, the Fourier transform, of course, is 2-dimensional, right? And so these time-varying gradients allow you to come and take samples of the Fourier transform in patterns that aren't just along the origin. So in other words, it allows you to come off and take samples in weird patterns, okay? Because you really need to get this whole 2-dimensional Fourier transform in order to take the inverse and get your image. Okay, so when people are designing MRI techniques, they're always thinking in this way. They're always thinking that their samples that they're taking physically are samples of what they call the K-space, okay, but samples of the Fourier transform. And they need to come up with a good way of sampling this pretty densely everywhere so that they can take an inverse and get a nice clean image. All right, and that's how the time-varying gradients come into play here. So here's examples of patterns that they might use to sample. Now this is partly why MRIs take so long, because they're actually sitting there trying to take all of these samples of the Fourier transform. And it makes a noise, right? When you're having the MRI, you hear like something going on. What does it sound like? A banging, okay. And those are actually like they're redoing. Each one of those generally corresponds to like a new path that they're taking through the Fourier transform samples. Okay, but the problem is that when they excite it, they can only listen to the signal for a short amount of time. They can't actually march through this whole thing and get the entire signal. So then they have to wait for it all to die down, and they have to excite it again, and cut a different path. Okay, and there's some interesting artifacts that happen. So this is fun. When they actually take these samples, the samples need to be close enough together. So I'm going to exit out of the slide for a minute just to add one more thing that has to do with this. The other thing in reality is S of t is sampled. So we said that you receive some signal on your antenna, and from that continuous time signal, you take an inverse Fourier transform. But in fact, this is sampled in discrete time. Okay, so discrete time. And the effect of sampling in discrete time is that in the Fourier transform space, you're only taking samples of the K-space spread out. You're not getting a whole line path, right? And if you spread them out too much, when you take the inverse Fourier transform, you get this. Now, we're going to talk about sampling today, and hopefully this is going to make a lot more sense. But this is the effect of aliasing. So you actually get this funny image. If you take the inverse transform and you sample too sparsely, you get this type of thing going on. Right? So my goal by the end of this lecture is that this makes a lot more sense to you, okay? Because we should understand sampling. I think that's about it for these slides. Just things about signal-noise ratio and stuff that I won't get into. Okay. Any questions about MRI? Okay, yeah.
Does it, when you're, like when you showed us the demonstration of like the different slices that's playing over time, like
yeah.
on the page, is it actually taking like individual slices, or is it taking the whole thing at once? So like individual images being calculated at once, or?
You know what they're doing? The usual thing they do. They could do it all at once and still get a 3D model. But what they usually do is they do one plane at a time. And the way they do that, if I pop open this again, the way they do that is they only, so when they excite it, they actually put a gradient, let's say, along this direction. They put a gradient already before they excite it. Now, in order to excite these strings, it's like if I had a string instrument and I want to excite it, I could either just make a loud popping sound and that would contain kind of all frequencies and it would start vibrating. Or I could play some very narrow pitch to it. And if they're in tune, it's going to start vibrating. But if they're sufficiently out of tune, it really won't vibrate much. Okay? So what you do here is you put a gradient in one direction. That way when you excite it with a narrow band of frequencies, only this plane basically will get excited. So they image one plane at a time. They don't have to do it that way. That's just the way they usually do it. Some of the reasons why they do certain things in MRI have to do with, this technology has been around for a few decades, and some things were easier to do mathematically and computationally than others. Like the Fourier transform is very quick to compute because you have a fast Fourier transform algorithm. So a lot of the reasons why they design things certain ways are so that they can use tools that are fast. Okay, so let's talk about CT. That's CAT scan. It's computed tomography. So this is actually X-rays. The way a CAT scan works is X-rays. Okay, and X-rays are very simple to understand. So this does X-ray, and it's also a 3D imaging technique, right? Okay. So X-rays just work by casting a shadow. So to understand X-ray, you just have to think about shadows, right? So for example, bone is more, it absorbs more X-rays than other materials in your body. Okay, so that means that if you pass X-rays through a body, then the bone will absorb more and you'll get a bigger shadow. All right, it's that simple. But CT is a little more interesting. What you do for CT, well, first let's draw a picture of X-ray. So let me do a two-dimensional object. Let's say you have okay, and you shine some X-rays down like this in one direction, and you have some film or something that senses it down here. And what you're going to get then is intense spots here where there's no shadow, and then when you get to the bone, it's going to be like something else, and you get some. I'm graphing the intensity you pick up on your sensors, right? But we can write what that is mathematically, that this function, this is basically going to be, so let's say you have a two-dimensional object. Of course, it's really three-dimensional, but let's say you have so your signal here, I'll call it measurement 1, M1 of x is going to be a function of what we actually have is some coefficients of absorption. I'm going to use d again here, d of xy. This is what we want to know, so this is our absorption coefficient. And what we get then is we get an integral of this along the y direction. So we get some base intensity that we would get if nothing was there, minus this, something related to the integral of the absorption. All right, so because what's happening is the light has to go down the whole lines, vertical lines, and get absorbed the whole way, right? In fact, there should be multiplicative, and maybe we need the log domain because, as it gets absorbed, instead of sums, you're getting products of absorption. But anyway, it's not really going to change things. We can just change the intensities to log intensities, all right? So you get something to do with this. So this is what we want to know. We are trying to image D, right? That's all we can get out of the X-ray, this contrast that comes from different absorption coefficients, right? And what we're given in each measurement, we're given a measurement like this. We're given an integral along a direction. Now, the idea of CT is that you do this along many directions. All right, so that was just one of our measurements. You're then going to come along and you're going to go horizontally, you're going to go diagonally, and you're going to then want to piece together all these measurements to get an idea of the three-dimensional object. Okay, and that's what tomography is. And the actual mechanism for doing that is not going to. I'm going to explain how to understand this information on an intuitive level, and a mathematical level. It's not really the algorithm used to reconstruct. In fact, the algorithms are pretty simple. You can do some iterative things to fill in, try to figure out what those densities are that would have given you the measurements you got. Okay, there's a lot of ways to do this, but still there's a nice intuitive understanding that comes by thinking about each of these measurements. We should recognize this thing here. This I can rewrite as the integral of dxy. I can put an e to the minus I 2 pi 0, let's say x, no, y, 0y, dy. Okay, that's not different. But now it looks like a Fourier transform, right? At least, so this is, integral from negative infinity to infinity. Okay, now remember that we said that, so this is what I want to say. What if we take the Fourier transform of our measurement? So let's take our measurement, M1, and look at this. Let's say M1 of fx equals the Fourier transform of our measurement, M1 x. Okay, and we can write that out here. It's the integral Okay, now we can plug in what our M1 is, written in the way I wrote it here. Now, this should maybe remind you of this DC component trick we talked about just before the midterm, that the integral of a function is the Fourier transform at frequency 0, and that's all I've done here. I've written it as a Fourier transform at frequency 0 along a certain direction. Okay, so what that means is that we can say that this equals, now I'm going to, of course, that intensity part is, it's going to be like intensity times a delta function or something, dfx. Okay, that part I don't really care about. Remember that this measurement, we didn't really care about that intensity. We cared about this other part. We could have subtracted off the constant intensity, right? So the point is, it's an integral of an integral of m1. It's an integral of an integral of dxy e to the minus I 2 pi 0 y plus fx x dx dy. And so that equals the Fourier transform of D. I'll just use capital D to represent the two-dimensional Fourier transform of D, evaluated at fx, evaluated at fx and 0. Okay, so one measurement, one X-ray measurement in CT is giving you the values of the Fourier transform of what you want. We want dxy. If I take the Fourier transform of my measurement, this is in a lower dimension, right? This is a one-dimensional thing. Take the one-dimensional Fourier transform. That gives you exactly one slice of the two-dimensional Fourier transform. So let's say this is d of fx fy. Okay, this is the Fourier transform of what we actually want to know. It lives in this space, and what we're saying is that the first measurement that went vertical gives us the values of this Fourier transform along this line. So we just sampled it, the Fourier transform along that line. Okay. Again, the intuition is when you integrate along a direction, that is evaluating the Fourier transform at the zero frequency along that direction. Okay. So then we get our second measurement. Let's say we come back up here, and now we get a measurement this way. And we get some, we sense it over here. We get something like this. Okay, we get a new measurement, and the math would tell us that that is exactly this sampling of the Fourier transform. So we sampled the 2D Fourier transform in another plane. Now really this is three-dimensional, so really each image, each measurement we get from the X-ray is a two-dimensional signal. We take the 2D Fourier transform, and that gives us one plane of our three-dimensional Fourier transform. It gives us one plane that passes through the origin. And in fact, by the symmetry of this Fourier transform, we also can get this direction here. We can sample the Fourier transform this way, and the way we do that is we just take an X-ray in that same direction. These are called projections. So this here is called a projection. It's a projection of D onto a certain plane. And this here, we're actually just taking slices in the Fourier transform space. So the idea is you do this in enough directions, and you end up getting a pretty good image. You slice this up in so many directions, and you take samples. You get a lot of information about the Fourier transform. And in the end, you can't do it in every direction. So you somehow have to interpolate the information you don't have. And you use things like knowing how big the object is and various things to interpolate the stuff you don't have. Okay. So from an information point of view, this is a good way to understand how computed tomography works. Algorithmically, you don't usually actually do it through the Fourier transform, as far as I know. Oh. Of I, you're saying this I, or? Oh, yeah. It's just saying if you have nothing in the CT, you're going to get light because you're shining X-rays. You're going to get some base amount of light, of X-ray that you sense, right? And what's happening is the object is reducing that intensity. So really, like the D is that you're trying to measure is actually like a reduction of intensity caused by absorbing X-rays. Exactly. So I mean, really what you would first do is just process this out and say, okay, get rid of the background light and just look at the difference of the light, right? Okay. All right. I'm not going to talk long about this, the third imaging, because we need to move on to sampling. But the third one I would have talked about is ultrasound. Does anyone know anything about ultrasound? How does that work to give you images? Well, what is it? Sorry, what? Yeah, it's like echolocation. So it's very much like radar. Echolocation, these are easy to understand. So whereas X-rays are shadows, ultrasound is reflections. And that's the same thing you do with radar. You shine out a signal and you listen for what reflects back. And based on how long it took to reflect back and so forth, you can get a nice idea of where it is. There's some interesting things to talk about here. The only thing I really would have mentioned for with respect to radar is you're going to broadcast a signal. Let's say some antenna. You broadcast a signal, and you have some object. Here I'm going to draw it like a car. And it reflects back, right, off of that object. But it also reflected off of other things. You had some building here. And you also get a reflection off of this. And there's a lot of information you can get by listening to the reflected signal. For one thing, it should take longer to get to the building if it's further away, right? So you can use the time between when you sent this pulse and when you heard it back, okay? Also, you get some interesting things having to do with the speed of the object because there's a Doppler shift if it's moving towards you or away from you. So the frequency of the reflection will change depending on its velocity towards you, okay? from a signal processing point of view, it's interesting that you usually design some signal, your pulse signal, that you want. There are various reasons to be careful about how you design this pulse signal, because you want it to be able to detect it easily when it's reflected back. And if we just call this, if we call it S of t, some signal you're going to send, it should be brief enough in time to get some nice resolution. So let's say you send some signal. Okay. Then it turns out that at your receiver, say you get some received signal, and you want to then identify these pulses in the received signal. Well, there's a method of doing this known as the matched filter. So, and that helps you identify exactly when this thing came in. Now, I should first illustrate why this would even be a challenge. Okay. Suppose you send some pulse. Well, the challenge is that there's going to be noise and interference in this signal. And when it comes in all noisy, you get some crazy noisy thing, and you want to know, uh-oh, I'm looking for this S of t in there. And I want to know not only that it's there, I want to know when it occurred. Then the match filter serves the purpose of detecting these. And what it is actually pretty cool. You just create an LTI system here, create a linear time invariant filter with impulse response that's S conjugate, of course if everything's real, then the conjugate doesn't matter, of negative t. So you make an LTI system where the impulse response is just the reversal of your pulse sequence in time. Okay, and if you do this, then what you can show is what'll come out is something that peaks right at the point of time where the signal is. So in other words, peaks locate S of t. So I kind of rushed through this, and partly because I told you I'm not going to spend a lot of time on this. We need to move on to other things. But we talked a couple weeks ago about the autocorrelation function. It was just very briefly. We said that if you convolve X with its time reversal conjugate, that's called the autocorrelation function. And you'll notice that that's what's happening here. If S gets received and goes into this match filter, it gets convolved with the time reversal of S. So what comes out should be the autocorrelation of S. And we said that the autocorrelation at time 0 is the energy. So what you find is that the energy of your pulse signal is going to be related to how high the peaks will be at the output of this filter. Okay, anyway, that was a very whirlwind tour of this. So we're done with these cool applications, and we're now going to get into one of the coolest, most important topics of this class, one of them, and that is sampling. Okay, so sampling is this process of taking a continuous time signal, x of t, and then you sample it, and out comes a sequence of numbers. So we've got something like okay, and we've talked about reasons why such a thing why you would even build such a device. Why do you think you would build a device like this? So let me just say this is in discrete time. Why would you sample a continuous time signal? Yeah. So you can store it digitally, and you can process it digitally. You can then feed it into a computer, a processor, some chip that's doing everything with digital logic, where you program in the math. The alternative would be to build something in continuous time that operates on your signal. If we weren't using electronics, you can still build the signal processor using mechanical objects, right? You can have springs and so forth process a signal. That's what the suspension in your car does. It processes the input signal to make it more enjoyable to the person in the car. So, but you can also process signals in continuous time with electronics. You can use resistors, capacitors, transistors, and build amplifiers that have the exact responses that you want. Okay. But it's often very nice from a design point of view to do it digitally, to have some mathematical processing you have in mind, and be able to just program it into a DSP chip, a digital signal processing chip. And to do that, you have to be working with samples, and you not only need things in discrete time, but they actually have to be represented with finite number of bits so you can store them in memory. Okay, we're just talking about the process of taking continuous time to discrete time. All right. Now, what you're going to want, though, is that eventually you're going to need to usually put this back into, reconstruct it to get it back to continuous time. So we'd have some XR of t, a reconstruction. Okay. So you've done a lot of work with discrete time signals in MATLAB. Everything we do in MATLAB is with discrete time signals. And but then you've played them back, right? You've done both the sampling without. I programmed that part for you in Shazam, right? That we can sample sound through the microphone, just using built-in commands, and we can also play sound out. And both of these are going to involve this process of sampling and then reconstructing a continuous time signal to play it back out for whatever purpose. If it's sound, then it goes out of a speaker, right? And the question here is. How can we construct this so that what comes out equals what went in? And can we? We certainly lost a lot of information. Now let me show you here what we meant by sampling. Not only did it came out here x of t, but if we drew x of t, if we drew some x of t in, the usual method for sampling is that at these uniform places in time, you just take the value of your continuous time signal, and that becomes your sample. Okay, this isn't the only way you could possibly do sampling, but this is the way we'll talk about it here. So you just lose everything between the sample points. Right? You're just storing the value there. You can build circuits that do something like this. They use a comparator with transistors to decide where the voltage is at the input, and they use a clock to take samples. Right? So, can we recover? If there are no assumptions, then no, we can't recover. Right? But we'll find that there are some natural, simple assumptions that do allow us to recover. It should be. I found it surprising when I first learned it. I hope you do too. So let's just talk about reconstructing from these samples for a minute. Let's attempt to reconstruct. So one way would be to do the following with the samples. Just let the samples be. Just take your samples. And do what's called a zero order hold. You just do this. Okay, so this would be, remember, the reconstruction should be taking discrete time back to continuous time. So we took a sequence of numbers, and now we've created a continuous time signal just by continuing on that sample for the duration of the intervals, right? Making rects, putting rects everywhere. Okay. Well, in my picture at least, that doesn't look anything like what went in. So this is, let's say, fail. All right. Let's do another one. So here we can do, take their samples again. And we're going to reconstruct by doing, this time by connecting like this. Okay. This is actually called a first order hold. All right. And again, this is not going to be perfect, but it looks at least somewhat smooth. All right. I'm still going to give it this grade, but we'll. But actually, we should be a little bit fair here, because if we had certain assumptions about our signal, if we knew that our input signal actually was of this form or of this form, and we had the clock synchronized with it, right? Then this would perfectly reconstruct. So really, there are assumptions of the signal for which these reconstructions would be valid. Okay. But they're not going to be I mean, these aren't the types of signals we expect to encounter often in continuous time. Okay, so we're going to find a more interesting reconstruction. By the way, these both can be explained another way, and that is, remember that we have a continuous time way of representing discrete time signals by just replacing them with delta functions, right? So, in other words, we can take our continuous time, we can take our discrete time signal and we can put delta functions in place of each sample and call this thing, now it's continuous time, but it's like our continuous time representation of a discrete time signal, right? If you convolve that with the rect, okay, you'll get the zero order hold. All right. In fact, if you convolve it with, so that's this. If you instead convolve it with this, all right, then you get the first order hold. Okay, so in fact, these are simple, mathematically simple reconstructions. Now, this whole idea of filling in information, because we're assuming we actually know the values at our samples are correct, right? So, but we don't know the values in between, and this is known as interpolation. So really what we're asking when we ask about reconstructing is, what's the right interpolation approach between our samples? If you're familiar with interpolation, there are lots of ways of doing this. If you do like graphics and stuff, people like splines and all sorts of interpolation approaches, but let me propose another one that we're going to like in this class. That is that we take our samples, and for each sample point, we take a sinc function. Let me do it like this. A sinc function that has height equal to that sample point. So we replace the samples with a sinc function. We do that for each one. The drawing becomes messy. Oops. Okay, you get the idea. Okay, so we replace each sample with a sinc at that height. And we add all these up. Okay, so this is called sinc interpolation. I'm going to say pass just for fun, because this will be a very useful method. All right. This is equivalent to convolving with sinc. Whoops. That gives us our sinc interpolation. I've just drawn it out another way, what convolution with a sinc would be, right? It's just going to, remember, convolving with a delta function is just moving your signal to that delta function rescaling, right? So what I've drawn here is exactly convolution with a sinc. Now, what is this going to look like when we're done? Well, first of all, it's going to be something very smooth, not like these first two examples. Okay, it's going to, first of all, it is a valid interpolation because at the samples, it stays unchanged. Why? Once I add all these sinks up, how do I know that they're going to be correct at least at the sample points? Yes? Yes, has zeros at all the integers. So all of the other sinks, so let's say we're concerned about this sample point and we want to make sure that the other sinks don't contribute to some error here. Well, all of the other sinks have nulls there, right? There's 0. So when you add them all up, it does not change the value of this final result at the samples. So at least we are doing interpolation. We're keeping it at the sample points the same. But when we add these up, we're going to get a nice smooth connection between the sample points. Okay, so that leads us to understand why. Let's talk about why this is good by first talking about the sampling process. We were talking about the reconstruction process here, but let's talk about the sampling process. Okay, so sampling, we're going to think of sampling in the following way. X of t comes in, and we're going to think of it as a multiplication with a pulse, with a sequence of pulses that occur at the points where we're trying to sample. So what we mean by this is the following. P of t equals delta functions that occur at the points where we're sampling. For now, let's just talk about sampling at a rate 1. Okay, so every sample, we're just sampling at the integers. So that means this is delta t minus k for all k. Okay, it's a delta train. It's like this. Okay, this signal here, we call this a delta function train. Okay, it's just a repeating delta functions with a certain spacing. All right. Now now imagine that you take your continuous time signal and you multiply it with these pulses that are occurring. Well, we already have a simplification that if you multiply a continuous function with a delta function, you just get it's equivalent to following. I think if I write it, it'll make more sense. X of t times p of t equals sum over k. X of t delta t minus k equals x of k. X at those integer values, t minus k. And in picture, this will make more sense. What we're saying is that if we have our x of t and we multiply it by these delta functions, the result is simply delta functions at the height of the function x. Yeah. So you see that I'm going to draw the green back up here. Okay. So you see that what we have is now a new train of delta functions that aren't the same height. They're the height of the function x. What? It's the samples. So I'm just giving you a mathematical definition of what sampling does. Okay? That's all we've done. It's just what you think of for sampling. The heights of these are your samples. Now, in reality, samples are a discrete time thing. And I still have this x here I have in continuous time because it's going to be easier to think about for the Fourier transform. Okay, what you would then finally do is replace. This is now our. So I guess the conclusion is xp of t is the continuous time representation of xn, which would be the sampled sequence, right? So it's just, we still have it in continuous time, but it's really just the continuous time version of our sampled sequence. Okay, now the cool thing is this. This is multiplication. We have a rule for multiplication. When we multiply in time, what do we do in frequency? Convolve. So we have our Fourier transform of x convolved with Fourier transform of this delta train. So we need to know, what is the Fourier transform of a train of deltas? Does anyone know this one? So this is one of those wonderful cases where it's the same exact thing. Okay, so a train of deltas is a train of deltas in the frequency domain. We have a few of those nice cases. In fact, in your first problem set, the bonus question was, can you come up with eigenfunctions for the Fourier transform, which is the same as saying, can you come up with signals where when you take the Fourier transform, you get the same thing back, up to possibly scaling. And this would be one example. Okay, another famous example is the so-called Gaussian distribution function. When you take the Fourier transform of that, you get the same thing back. Okay, so this is key to our understanding of sampling. Okay, this is very important to know that the Fourier transform of this sequence of delta functions is the same thing. Okay, so what does that mean? Let's say in the frequency domain now we have something f. This is our x of f. Okay, it's our continuous time signal, the Fourier transform of it, and we are going to convolve it now with delta functions at 0, 1, minus 1, so forth, in the frequency domain. Well, this should be easy enough. It's not as easy as multiplication, but it's convolution with delta functions. So what we are going to get is we're going to get something that in picture looks like the following. We're going to get what we had there. Okay, let's say centered at 0. I'll give it some scale here. We're going to get another copy of it like this, where at 1 hits the same point, right? So a shifted copy. We'll get another copy this way. Okay, and we're going to get all of these added together. Is that making sense, this convolution? Okay. Now, the problem is that when you add these together, we're going to consider that to be bad, okay? Because we now have different parts of our input signal that are indistinguishable once they've been added together in the sampling. This is aliasing. Yes? Yes, these are all x of f with different shifts. So I should say this is x of f. This here is x of f minus 1. And this here is x of f plus 1. You see that what we're doing is we're doing a convolution with each delta function separately. And that's giving us these shifted versions of x. And then they're being added together. And when you add them together, you kind of mix information from different frequencies. And this is aliasing. Remember, aliasing is going to occur in discrete time. There will be different formulas, sinusoids that are exactly the same in discrete time. And that's what we're encountering here, is that when we sample a signal, if there were two different frequencies in that signal that differed by integers in frequency, once you sample them, you can no longer tell them apart. That's what this picture is showing. It's showing that if they differed by exactly 1 in frequency, now they line up once it's sampled. They get added together. Okay. So the key idea here, if you want to be able to reconstruct, is that your sample, suppose x of f looks like this. Suppose that it's between, let's say, a half and minus a half. in frequency. It's band limited. So that means that it's band limited to the set of frequencies between -0.5 and 0.5. Okay. By that we mean that the magnitude, that the value of x of f is 0 outside of that band. Okay. Then when we do this convolution, we're going to get copies 0, 1, -1, so forth, but they're going to look like this. Now, I color them just to show how I constructed it, but of course, when you take the Fourier transform of your sampled signal, it's not going to be colored, right? You're not going to know which parts came from what. It's just going to be the sum of all of these things. But here, because we knew that the original signal was band limited, then we have not lost any information by sampling. Okay? Is there some way now that we might recover our original signal from the sampled one? So, of course, these are different. They're different, but it's a reversible process. If we could remove all of the extra parts, how might we remove all the extra parts? So suppose now that we take our xp of t, the sampled one, and we put it in to a low-pass filter. So we'll say low-pass filter, something that we will talk more about, but you should know generally what this is. Let's make it have a cutoff of 0.5 and -0.5 and a height 1. Okay, what does this mean? This means that take your Fourier transform, and what we'd like to do is multiply it by something like this, by something that cuts out everything except that first region. Okay, multiply it by an indicator function, by something that's 1 only in this range from 0.5 to -0.5 and 0 everywhere else. Yes? Oh, a high-pass filter would kind of be the opposite. It would be 1 minus this green function. So it would just pass everything else. Yeah. So if we pass it through this low-pass filter, and what I'm talking about now is I just want to go remove everything in frequency above 0.5 and below -0.5. But we know how to do that. That's a multiplication with a rect, right? A low-pass filter is exactly multiply. This is our x. This over here, remember, is x p of f. So it's the sampled version of x in the frequency domain. We want to multiply that by a rect. Okay, a low-pass filter. What does that actually mean we do to x in time? What? Convolve with sync, right? Multiply by rect in frequency. Ideal low-pass filter is convolve with sync in time. So if we do this low-pass filter, first of all, you can agree by this picture that as long as our original signal was band limited, that the result will be back to what we started with. We'll get back to the original signal, right? Because it was band limited. And so what will come out here is x of t, the original thing. Good. We interpolated correctly. And as we just said, this process is the same as convolving with sync. So now we've just derived this reconstruction, sync interpolation. Okay. So if it's band limited, you can reconstruct with sync interpolation. The only thing you need to know to do there is a question in the problem set about sampling. And some of you would like to get started before Thursday. So let me just say that we've only talked about sampling at a rate 1. Okay, we've said you're sampling at the integers. Of course, in reality, you sample at a sample rate. You pick a sample rate. And what you're going to find is that the you could have used the scaling rule to get this. If you sample at another rate, delta t minus, and now what we're going to have is k over f. So if f is very high, then we're going to sample this. Yeah. Okay. So let's say fs. So this is some sample rate. That's what it means to sample at a higher sample rate is to multiply by this train of delta functions. And the Fourier transform of this thing is just going to be, let me see if I can get the scaling right. It's going to be delta of f minus fs k. And there should be a scaling, which I don't remember if it's fs here. I don't think so, though. No. I'm going to put this, and I'm going to correct it when I put it online. But it turns out that the constant's not going to matter for your problem set, right? So if you sample at a different rate, then you just have to adjust this picture. You're doing a convolution with a different train of delta functions. They'll be spread out now rather than at the integers. They'll be spread out by the sample rate. Okay, and so you have to do the same picture and see, do you get aliasing or not? And we'll say next time that you get to this Nyquist frequency that you guys have all heard about.